Hello, welcome to this lecture. We have earlier seen the lecture of circularity indicators, and we are continuing on this line of, let's say, a broad introduction or discussion about circular economy. And now we are going to talk about eco-design in this lecture. Okay, so I have structured the lecture like this. First, we are going to see the different definitions of eco-design. And then we are going to see what's called as the golden rules of eco-design. And we are going to take a particular zoom in look into the concept of longer lasting products and the concept of obsolescence. And then we are going to go into a case study where it's on wooden doors. But what I would ask you to do is not to really pay a lot of attention of the particular case I am presenting, but rather how the case has been handled, what are the concepts that we learned has been applied in this particular case study, and how they used LCA to sort of arrive at a conclusion of how to make something better through eco-design. And one thing we are going to see in this particular case study is that it is not about arbitrarily choosing something because we feel that it may be good for a particular system, but quantitatively knowing something that something could be bettering a particular system through eco-design. And then we are going to present a summary and conclusion. Okay, so there are many definitions for eco-design, just as they are for circular economy and for other things. And let's look at the first definition. Eco-design is simply a good design and good business practice. It's a way of thinking and doing. Okay, this definition doesn't give us anything actually, so it's pretty vague. And let's go on to another definition which could give us something a bit more concrete. Eco-design systematically incorporates environmental decisions into the design process. So taking environment into account is one of the key factors of eco-design. It's already covered. So you have the life cycle thinking, and then the aspect of decreasing the environmental impact by designing, and then always considering environment as a requirement in the design process itself. So these are the concepts, key concepts for eco-design as put forward by Sustainable Mains. Okay, that's a good definition. It's detailed, it's specific. Are we still missing something? In my opinion, the European Commission EC's definition of eco-design really covers something very important. Of course, you have to take environmental impacts of a product into account in the very early stage of designing something. But what you should do is to avoid uncoordinated planning. Okay, we are going to see example of what's uncoordinated planning through the example that we are actually presenting. So see the example EC gives here. For instance, eliminating a toxic substance should not lead to higher energy consumption, which on net impact could have a negative impact on the environment. So always having this sort of thinking in systems approach so that we take everything into account and we arrive at a net positive impact on the environment. That's more or less, I would say, the concept that we are talking about. Okay, let's come to the slide of 10 golden rules of eco-design. So on the left, you see the 10 rules. On the right, you see a student project which tried to apply these 10 rules to a particular product. So let's first take a good look into the rules. First thing, don't use toxic substances. Of course, this is also a key rule in the 12 principles of green chemistry. So try to minimize or try to avoid using toxic substances, and then minimize energy and resource consumption in all phases, not just the production phase, but also the use phase, something that we have already learned about in our previous lectures. And then use less weight to deliver the same functionality. That could be one of the important things. And then try to promote repair and upgrading within the context of the product that you produce. So if you produce a cell phone or a computer, whatever, try to promote upgrading and repair. And also try to promote recycling by sort of labeling the stuffs. For instance, there is a lot of debate about creating battery passports, and how can we effectively recycle battery materials is a debate that people are having now really fervently. So trying to label things precisely helps makes recycling really easier. And also try to elongate or really lengthen the product lifetime. So that's something that we have also already seen, and try to incorporate recycled materials into the production process. And last thing is try to use few joining elements as possible. It's interesting that I have also worked not just in recycling in my PhD, but also in the 10th point. I'll give you an example. So there is the issue of using really heavy weights in marine environment. Really, let's say the nuts and bolts that we use in marine environment could easily be corroded. So people are thinking about replacing these really heavyweight structural materials with sort of adhesives rather, which can bind steel and composite. So by doing that, you reduce the weight in the ship, but also you reduce emissions, for instance, because of the fact that you aren't using that much of structural materials. So interestingly, you can also try to use few joining elements, and these are more or less the all the golden rules of eco design explained. But read through all of them, but you already know all of them, in my opinion, because we have attended the classes before, we have talked about the rules in one lecture or the other. But it's good to have these set of principles, let's say, bolted down one after the other. So what this paper also contains is different student projects. It's quite simple. People from a university they have taken a product. It could be, in this case, a squeezer, and they have tried to apply all these rules one by one and see how they can actually improve a product. So take it as a challenge for yourself. Take any product. It can be really a small thing like a mobile phone, or it can be a large thing like a ship, or it could be an aircraft, spaceship, whatever you feel comfortable in. But it could be something really small and you use every day. It could be a knife. It could be anything that you can imagine. And try to see how you can apply these rules of eco design. And maybe you don't need to find a way to better by every rule, but even in few rules, by using few of these rules, if you are able to better the performance of a product, it's already great. So do this as an exercise. It would be really illuminating for you. Yes. So I will post this example PDF to you so that you can actually take a look at how people have tried to improve the products through eco design, but come up with your own, let's say, projects or examples. It could be very simple. You can take a product which is something that you use in daily life and then apply these principles and see what happens. Okay, so these are the 6 rules for longer lasting products. Long lasting products is a zoomed in look into one aspect of eco design. And this was given by Marcel Hollander in his PhD thesis, and he did his PhD at Delft University of Technology in the Netherlands, where I did my PhD as well. And I attended one of his talks or read something about it, and I found this very interesting. So it's a really easy pyramid. The first thing to do is to create trust so that the consumers or the customers come back to you for repair, refurbish, remanufacture, for instance. And then try to create durable products. Do not plan what's called as obsolescence. So for instance, trying to make sure that the product becomes non-functional as soon as it can so that customers have to buy a new product is not the best way to go, but rather try to make durable products which last long for a longer time. And try to design for standardization and compatibility. Whenever you have standardized parts in a product which could be easily replaced in the case of an upgrade or a repair, it makes life easier. And try to make the maintenance and repair part as easy as you can when you are designing. Do not try to make dismantling so difficult so that you can not actually easily repair. And try to make it easy for upgradability. Sometimes you have entirely new product design that's coming up, so try to see if you can design a product in a sense that it can get upgraded in the future in case of radical new thinking coming into product development. And try to make it easier for complete disassembly and reassembly into a newer product. If you actually look at these rules, from top to bottom, the entropy increases. So you have this sort of, it's similar to Stahel's inertia principle, okay? Do not repair what you can, do not remanufacture what you can repair, and do not recycle what you can remanufacture, and so on and so forth. So you have the order of entropy increasing throughout from top to bottom. So that is also something that you could observe in this particular pyramid. So he created a sort of three-dimensional plots to understand obsolescence and to improve a product design. Hearing it sounds complicated, but listen to me, it's quite easy. I'll explain it to you. So obsolescence, as I already explained, is trying to make sure something is expiring or becoming non-functional as fast as it can. And what you have to do in a circular product design is to resist this concept of obsolescence. So you can do it by three ways in Marsa Hollander's opinion. First is by resisting the obsolescence. So you design for more durability, or you can postpone the obsolescence. So if you design for maintenance and for repair, you kind of postpone the obsolescence. And you can also reverse the obsolescence. So if you design for remanufacturing a product or refurbishing a product, so you can reverse the obsolescence that is already existing in the product design at the initial phase. So you guys told me that I have to give you examples, not just the concepts. Let's take a look at examples for you. Okay, so let's get into the examples. It's very interesting to understand these examples. It's quite simple and it's fascinating. I'll explain it to you. So he created these three-dimensional plots. Okay, so see here, there are three axes: resisting, postponing, or reversing obsolescence. Three different ways to challenge obsolescence, right? And you can imagine a throwaway product, that is a use and throw product as they call it, is literally the worst. So you have it right at the origin, which means that it is not challenging the concept of obsolescence whatsoever. So if you could agree with me, the throwaway products really lie at the origin and are literally the worst in challenging obsolescence. Okay, so we are going to see two different interesting examples. He has many other examples, but I chose these examples because we have already seen them in different contexts. For instance, the initiative of Fairphone. Okay, we already know for a fact that mobile phones last 2 years in the European market, or in the US market for that matter. We saw this in the circularity indicators lecture, remember? So the Fairphone product manufacturers have come up with this idea of sustainable mobile phones initiative, where their idea is to have longer lasting phones, for instance, at least 5 years instead of 2 years. How do they do it? How do they try to have this maintenance part? They make it easier for upgrading the phone. They also try to make sure that they are making it easier for repair, for instance, by creating designs which can be easily disassembled and to be repaired. That's how they are actually challenging obsolescence. So in which quadrant they are? They are in the quadrant more to the side of postponing obsolescence, of course. So they are, instead of lasting a product for 2 years, they are trying to make sure that the product can last long until 5 years by ensuring that it can be repaired fast or it can be upgraded when sort of new things come up in the market in product designs of their mobile phones. So that's how they challenge obsolescence. And the Miele washing machine, we also saw the washing machine in the remanufacturing lectures in different contexts. How they resist, how do they challenge obsolescence? They do it by actually making the product so durable. So instead of lasting long only for, let's say, 5 to 10 years, they try to make sure by using really high quality components, the washing machine is supposed to last long for until 25 years. So by ensuring great durability, they are making sure that they are challenging obsolescence. So they lie in this quadrant of resisting obsolescence by increased durability. You can also come up with different examples for reversing obsolescence using refurbishing or remanufacturing. I can post a link to his thesis and you can see what are the other examples Martha Hollander comes up with. But in general, to preserve the product integrity, these are the kind of initiatives you can do to make sure that you're challenging obsolescence. Okay, having said all these things, what we have seen thus far is sort of a definition of eco-design and the key rules of eco-design. And we also took a zoomed in look into longer lasting products and how we can challenge obsolescence. Let's take a closer look into a case study. Okay, it is about interior wooden doors in non-residential buildings in Canada. Such a boring topic, I will also agree. But what I'm more interested in is not on the doors, of course, but on the fact how you can actually apply these concepts to that of the improvement of this particular product. Okay, so in this case study, there are two parts. The first is to try to define a system and then to break it apart into different components and different stages of operation and then quantifying its environmental impact. That's the first part. The second part is what we can do about it. It's trying to apply the eco-design principles to improve the product. So we chose a system of wooden doors. Building sector really represents a lot of global resource extractions, and if you use a steel door, that has more emissions than even the wooden doors. So what they have tried to do is to use LCA, life cycle assessment, from cradle to grave. Again, I think you have been introduced to LCA by Professor Akhtan and by others in EGAT. So I'm not going to really go into the basic definitions of LCA. So it's basically used to assess the environmental impact for the whole life of the product, right from the raw materials to the disposal. What we are going to do is to quantify the impact of all these chains on various different categories on environment. So that's the first part. So this is the closer look at the system. You have front and the rear, and then you have a core. That's basically about it. You don't need to really memorize the door structure, but it has two faces and a core, and the faces are made up of hardwood veneer and fiberboard, and the core is made up of particle board. The adhesive is polyvinyl acetate. So you have two faces, a core, something to bind it with. As simple as that. These are the different things that has actually contributed to making the door. Okay, so what are the stages of this product making? So you have the raw materials, and then which is made into door components, and then the door components are taken into making a manufacturing of the door. You have transportation, very important, and then you have the use phase, and then you have disposal or landfill. Okay, cradle to grave. So the life cycle inventory is basically used to quantify materials and energy flows that goes through the entirety of the system. So you have a lot of databases. To have, let's say, a comprehensive database is really crucial. And in their results, LCI life cycle inventory results, these are the midpoint categories and these are the damage categories. Essentially, you have human health, ecosystem quality, climate change, and resource use, right? So you have all these sort of toxicity, eutrophication that we have already talked about in ecosystem, and then everything that has to do with health in, for instance, human toxicity, respiratory effects goes into this particular damage category. And we know also about climate change and the resource use. So these are typically the damage categories and typically the midpoint categories when it comes to LCI. Okay, so what have they found from their LCA? They have found that basically raw materials are responsible for a lot of impact on the human health, and it's almost 70 percentage. And they try to zoom in into this raw material category, and they find out that particle board is one of the major culprits. So basically it uses a urea, a formaldehyde resin for production. So you have to have, these are thermosetting resins. So basically they get really hardened during the curing processes, and they are essential to bind different stuff. So in this particular case, it's the urea formaldehyde resin, which is having a lot, huge impact. Transport, yeah, there is a contribution which is non-negligible. You have the NOx emissions from particulates, which are particular concern. And then landfill also contributes through the case of ozone layer depletion. So what you're essentially seeing here is the breakdown of contribution of different parts to the category of human health. And again, the ecosystem quality damage is basically down a lot to raw materials. How does raw material contribute to damage on ecosystem quality? You can imagine so many things, right? So the land use contributes to the damage, and also acidification, ecotoxicity, nitrification, all these things that are associated with extraction of raw materials and usage of raw materials. So all these things have a huge contribution to the ecosystem quality damage. And in the case of climate change, it's again the use of urea formaldehyde resin that is responsible for huge sort of emissions from the particle board. So you have the emissions not just from CO2, but also from CO, from methane. All these GHG gases have to be taken into account. So what you are essentially seeing is that you have to break down the raw materials into different components. It's essential for an LCA that you have all these different components effect taken into account. And once you try to do that, once you try to quantify the impact of everything, then you can narrow down really on the culprit and to see, oh, this is the thing that's giving me the worst environmental impact. So what can I do about it is the next question. So basically what you are seeing here is that instead of the manufacturing, the raw materials have maximum impact across all these categories, as we saw, in especially the particle board and especially the urea formaldehyde binder. So what we are able to do is that we are able to distinguish the impact between the manufacturing stage and the raw materials in the first place. So for instance, let's say somebody tells you that emissions from doors are this much, and then you go ahead and then you try to do a lot of shifting and changes in how you can manufacture the door. That is not very useful, because the impact is on something else, is coming from the raw material. So always you have to quantify the impacts first. And in the raw materials, you can change so many things, but you have to narrow it down to which one would be the most impactful and the prime culprit for such kind of damage. Okay, and the transportation from manufacturing to the stage of use, that also has a considerable impact. And landfilling has equal impact as well as that of transportation, as we saw from ozone layer depletion. So you don't need to know the particulars of how this particular wooden board is trying to have a negative impact on environment, but you need to understand the phenomenon of how they try to approach a problem. When you are trying to eco-design something to make it better, to improve it, to lessen the damage on the environment, the first thing you need to do is to break a system into its individual components, into its individual unit operations, and then try to quantify the impact on all these operations, on all these materials, and then try to think about eco-designing. Then come up with the strategies for eco-designing. Always put numbers on the tables, and it makes it really easier. Okay, so they tried to improve the system through eco-design by applying different scenarios. That's how you approach an eco-design problem. So I'm going to replace the urea formaldehyde adhesive, a chemical adhesive, with a natural adhesive such as pine tannin, grape tannin, or soy-based adhesive is what they imagine in the first three scenarios. Then they tried to replace the wood particles with wheat straw. They tried to replace, remember, transportation was a huge issue. Instead of road transportation, rail transportation. Instead of actually exporting the materials, let's have locally sourced the raw materials. And instead of landfilling, let's try to reuse and remanufacture the core, is how they thought about this problem. See, what you have to actually take a good look into this slide is how the principles of eco-design are applied here. You don't need to memorize or know what this particular study has done again. But what you need to know is how they thought about it, how they try to come up with these solutions and scenarios. Okay, that's more important. Okay, so using an alternative adhesive, what they find is quite fascinating. The first thing is in scenario 1, I think in pine adhesive, I guess, they have a reduction in climate change and in resources. They have reasonable reduction in both these cases. But in the case of soybeans, they actually find that it could be really worse because soybeans need diammonium phosphate and potassium chloride during its processing, which means that these things also have to be taken into account and their impacts also have to be quantified, which means using soybeans can actually deliver you really worse indicators in some of these categories. So the first learning lesson here is that instead of just believing that, oh, instead of using a chemical resin, if only we could be able to use a natural resin that we find, or a resin that is something derived from nature that we can just use straight away, it's completely wrong. It's not the correct way to go about it. What you have to always do is quantify. Knowing is really different from feeling. So instead of just feeling that this could be something better, always try to quantify, get the numbers, get the impact, and then we can think about which is the best way to go. As we saw here, soybean adhesives are not so great because of the ingredients that you need during the processing. And wheat-based straw, wheat straw-based alternative instead of the other ones in the wooden doors. That actually gave really hilariously worse impact on all categories. So again, once again, what do we know about that? Why is that really, really bad? Because using these wheat straw based alternatives needs a pre-treatment step with bleach at a really high solid to liquid ratio. And if you're going to use such kind of SL solid to liquid ratios with enormous amount of bleach before you can use these wheat straws, it simply means that you're going to get really worse indicators. So not just the material that you're trying to replace, but also how it is processed. Every step matters. Everything matters in quantifying the LCA. Only by taking into account these minute details or all the holistic information, you can arrive at an accurate picture. Because otherwise, you could really go to a completely wrong picture and then still have a lot of emissions. And what they found in the case of transportation is that if you actually think about using freight or rail transportation instead of a road transportation, you can have significant benefits within the category of transportation to have less environmental impact. So finally, they tried to reuse the core. Instead of using new cores all the time, they tried to reuse the core of the door, and then they saw how it can be beneficial. It showed really positive consequence. All the categories, the impact was drastically reduced, which means that this possibly is the way to go. It could be common sense to see, oh, if only we could reuse the core of the door again. But again, when you try to quantify, you clearly see the numerical benefits. And the more times you try to reuse the door, the less environmental impact it actually could provide. And then you of course reach a saturation point. But when you try to instead of just reuse once but try to reuse the product again and again, it could also have significant reduction in environmental impact. So they tried to quantify all the 7 scenarios, and I provided you the data for all these scenarios with different categories. Okay, these are the summary. Basically, the first adhesive gave us a little bit better results, but soybeans gave really worse adverse environmental impacts. Why did it do so? Because of the base chemicals that are needed for the processing. And the idea of simply replacing with the natural wheat straw, the agricultural fibers, was a terrible idea, because it has to go through a chemical pretreatment step which really has adverse environmental impacts. And the transportation change yielded some substantial results, but most importantly, we saw that the reuse and remanufacturing gave us the largest benefit. The reusing of the course multiple times gave us really the largest of the benefits. So we arrived at such conclusions only by quantifying the impacts of every single scenario that could be envisioned, and by making a conscious decision of what to do. Okay, so it's really a two-part series of papers, and it's very interesting how they go through from step to step. Always the step one is defining a system. Clearly defining a system is half the job done, because then you know what are the essential components present in a system, and then you can actually quantify its impacts. And then coming up with the principles of eco-design, what can we actually do to make the system better? We find the most important culprits and we try to change them with an alternative that we envision that could be better. And then we try to involve the core concepts of circular economy, such as reuse or remanufacture, and see if it actually makes lives better. And in this particular case, it really gave us a better result in remanufacturing, especially because you see for a wooden door, there is not a lot of use phase energy consumption like we saw in the case of washing machine or a fridge, right? So you can imagine how reuse and remanufacture could give a large benefit to such a system as well. So in conclusion, you can read through this conclusion, but I would essentially emphasize this part. Try to do the exercise and try to apply the eco-design principles for a product you know. That is most important than actually learning through what was done through the LCA of this particular study. Of course, you see the tangible benefits of eco-design already. I showed you how it can create less environmental impacts in every single category by applying some strategies of eco-design. And we saw that everything matters, every step matters, every chemical matters, every pre-treatment matters, all the unit processes, all the raw materials matter. If you neglect one over the other, then you are going to see really different drastic results than what you have seen. So for instance, if you neglected the pre-treatment part of the wheat straw, then you would see really a different result than what you're seeing now. So it's important to take into account everything. So in this particular case study, you saw that both the material as well as the engineering aspects matter. So you could try to incorporate both of these aspects to better the eco-design. Of course, eco-design is environmentally friendly and mostly cost-effective as well, but the devil is in the details. As I have always told you throughout the lectures, as long as you could quantify, as long as you could justify with clear categorical numbers and results, you could always try to use those things to better a system. Otherwise, doing something arbitrarily, thinking that this could be better because something feels natural or something is available in nature, and then by using it we could make it better, maybe that's not the case. So always quantify, always study the impacts, and then try to change in the best possible manner. So having said all these things, try to do the exercise. I hope you do this particular exercise of trying to eco-design a product and trying to come up with strategies of making the product better. It could really be useful for you, but who knows, you probably came up with a really nice design for a product that a manufacturer would use in the future. So try to do this particular exercise.